All right, everybody, let's simmer down. No, back from lunch, but we still got some interesting talks up ahead. So first off, we're going to have Zoltan from UNSW talking about the seL4 core platform. So thank you.
Oh, thank you, everybody. I am Zoltan. I am a lecturer in formal methods now at the University of New South Wales. I previously was at CSIRO when Trustworthy Systems was there. You might know me. I worked on the binary verification of seL4 on the RISC-V architecture. And I have come here today to talk to you about the seL4 core platform. Let's see if the slides work. I'll look at that. So this is not the first time someone gives a talk at the seL4 Summit about the core platform. Back in November 2020, Gernot gave I think it was an online talk, judging by the date, about seL4 CP. And that's short for seL4 core platform. And back then, we were just about going to release the RFC. And a whole lot has happened since then. So now, seL4 CP is implemented. You can go on GitHub. I didn't put a URL, but it's on GitHub. You can find it. You can clone it. It's used in-house. It's used externally. It's battle tested on 2 boards, so it now supports 2 boards. And so we thought, well, maybe it's the right time to revisit it. So what I'm going to be talking about today is what happened in those 2 years, how seL4 CP was implemented, how you can use it. And then I will talk briefly about my work, which is verifying seL4 CP, bringing formal verification to the core platform. And I think we can get started. Yeah, so start with a little refresher on what the core platform is, because some of you weren't alive 2 years ago. Some of you, well, most of you weren't here. You didn't see the talk. You don't remember. So what is the seL4 core platform? If you go on GitHub now, there's a blurb which says it's a simple operating system for the seL4 microkernel. More specifically, it is a simple, small operating system for embedded systems, cyber-physical systems, and IoT, built for creating simple static architectures. Now, static might be alarming for you, but you'll see there's dynamic possibilities. They're just not implemented yet. And why do we focus on these 3 things? Well, it's because that's by far the most common form of seL4 deployment in the wild, by a large margin. This is how seL4 is used, and we wanted something that supports the most common use cases. So how does the core platform help you do better work? It's supposed to make development and deployment easier and more user-friendly. We'll see how user-friendly it is. And by giving you correct, safe, secure by default ways for using seL4 mechanisms, so that you don't have to be an expert on the seL4 kernel to have safe and useful defaults. Everything out of the box in seL4 CP is designed to be correct. And keeping a minimal verified trusted computing base and doing that while retaining the seL4 kernel's superior performance. Because we have the fastest microkernel, it would absolutely make no sense to build something that's slow on top of it. So the core platform has performance first, and ideally you won't even notice that it's there. It will give you the superior performance by default. Okay, where does this fit? Where do you use it? Well, seL4 CP gives you a minimal, reasonable policy layer on top of the kernel. As you know, the kernel is user policy free deliberately. And it gives you a very simple API against which you program, and you get a reasonable degree of application portability. It's built fully on the MCS kernel. It doesn't support anything else. We think MCS is the future, so we're building on top of it, but you can use it today. And what I like best about it is, unlike other similar systems such as CAmkES, it allows you to BYOB, bring your own build system. It is an SDK. You get it, you integrate it into your build system. You don't have to care about how it builds, and it doesn't care about how you build. You get your application ELF files in any way you want, and as long as the ELF supports the very minimal binary interface that seL4 CPU requires, seL4 CPU will be able to load and use your binary, and you'll be able to use this as part of the systems that you design. So basically what I said, here's what it looks like. You create your ELF files. I'm not sure if people online can see my hand, but yeah, I can't point at it in any other way. So you build your ELF files. Here comes your build system. There's the core platform SDK. The core platform SDK is not going to care how you get these. You can get them any way you want. What you give to the SDK tool is your compiled ELF files and a system description, an SDF file. SDF stands for System Description Format. Remember that. It's going to be important in a moment. You give all this to the SDK tool, which is just a simple command line tool. You can invoke it on your favorite development system, and it's going to get you the seL4 kernel. It's going to get you 3 components that we'll talk about in a minute, and it will generate a system image that you can load into any supported board directly. Or you can continue with your build however you wish, however you get this to your users. Again, it doesn't care. There's no monolith anymore. There's just a simple tool, these 3 components, and it generates the system image and integrates with how you build. Okay, so what are these 3 components? They're a system initializer, a monitor, and a library. A library is what you program against. It's a single include H file. And the system initializer is a init task. It's not a kernel boot task. It's an init task. It's what seL4 drops into when your system starts, and it looks at your system description, starts your ELF files, distributes the capabilities that they'll need to them, and then it becomes a monitor, which is just a fault handler for all these ELF files and so on. And that is all that it consists of. It's an extremely small system. The initializer is about 1.2 thousand lines of code, and the monitor is less than a 1,000, and the library is extremely small. It's less than 500, I think. It's basically a thin wrapper around seL4 kernel calls. So the interfaces for all this are extremely simple. I don't know how well you can read the text from back there, but you have your code. It implements 2 functions, 3 functions in the worst case, and you have an SDF file which describes the protection domains, which are like processes that your system consists of, what else to load, shared memory regions, and channels. I am not going to talk about these abstractions that the core platform provides in any great detail today. Memory regions, protection domains, and so on are outside the scope of the talk, and that's because you have 3 good resources for them now. You can watch Gernot's talk online from 2020, where he explains all 3 abstraction mechanisms that we have. And you can read the documentation on GitHub, because again, this is implemented. This is something that you can actually use today. And finally, you can come along to Ivan's workshop on Thursday and play with it there. So there's no point in me explaining these abstractions now. They're very basic, very simple abstractions. So again, we have these two parts: the library, the init task, and the monitor. And the init task simply executes your invocations to create and configure kernel objects, distribute caps in accordance with the specification you created, and after init, it just acts as a fault handler for all the protection domains that we started. The library provides functions for handling the 3 abstractions that you've seen on the previous slide: memory regions, protected procedure calls, IRQs, and so on. And the build tool is not something that you run. It's something used to build your system that implements the generation of the system image based on the ELF files and the system description. So on an architecture diagram, it really acts like an operating system abstraction. It sits between the kernel and the application. You'll see drivers here. So there's mechanisms like IRQ handling that you can do at the core platform level. And Lucy will talk about the driver framework in the next talk, I think, right after mine. So you'll hear more about drivers. And that's all nice, but I started with saying that this is going to be super user-friendly. Again, on the 13th of October, you'll be able to experience it yourself at the workshop. But I can tell you that seL4 core platform has undergone the strictest usability testing the planet has ever seen. It is true. This is it. It's me. I can't install anything. Give me Git, I'm completely lost. And even I'm able to get it to work with a little help from our students. So, but it's not just usable, it is used. What happened in the last 2 years while we were implementing the core platform is that our friends in Breakaway, who actually implement the core platform, and Filmmaker, who was at EDS at the time, and Gernot got an ICERA grant from the Australian Department of Defense for developing a little device called Layout. I'm never sure how to pronounce this. It's a protective device for critical infrastructure, and it was implemented together with the core platform. And engineers who've never used seL4 for anything before have worked on it and were able to use it successfully. So it's not just user-friendly, it's not just usable, it is actually being used. Now, that's all fine. You can try it out on GitHub, and you can check out Layout at, this time I included a URL below. There's a lot of resources on it. But none of this is my job. I'm not implementing seL4 CP, that's mostly Breakaway. I don't do hardware stuff. I am here to bring formal verification to the core platform. So we have our formally verified kernel already, and we have a bunch of new stuff, and we'd like to enjoy the benefits of formal verification throughout the whole stack now. So thanks to the UK's National Cybersecurity Centre, I got some funding to work on this and verify the seL4 core platform. And since there's 2 components that need to be verified, the system initializer and the library, well, step 1 is to verify the initializer, and step 2 is to verify the library. And if everything goes as planned, we'll have both of these by March next year. So how is this going to go? Well, first we have to verify the initializer, and the good news is a large chunk of the problem has already been solved. There was a DARPA Cyber Assured Systems Engineering project, and TS, as part of it, produced the verified so-called CapDL loader, which is very much like the core platform system initializer, in that it can boot an seL4 system as an init task into a capability distribution state defined by a CapDL file. Now, this sounds like it almost solves the problem already, except while other systems such as CAmkES use CapDL, seL4 CP uses its own system description format SDF. And there's very good reason for that, because it's quite easy to write SDF files by hand, and it is something that we expect the user to produce. Whereas CapDL is a different language which wasn't really designed to be used by hand. I had to write some by hand as part of this project, and it's no fun at all. Instead, it's usually generated by some other tool, like a CAmkES outputs CapDL and then uses a CapDL loader. So how do we leverage this pre-existing work on verified system initialization? Well, we have to translate our SDF directly into CapDL. And then we can just use the pre-existing CapDL loader to load our system into the capability distribution and configuration that we want. So the way it works now is the user writes the ELF, the user writes the SDF. Again, this is the system description. Then the SDK configures a system initializer task, which is this custom-built code implemented by Breakaway for the core platform. And the core platform starts your system and does all the tasks that are required to bring your system into the SDF specified state, and then drops out and acts as a monitor. But none of this is verified. This is just a piece of code. It's a nice, well-written piece of code because the people at Breakaway are really good at programming. But there's no formal verification. We don't know that your system actually starts in the state that you specified in the SDF. In the future, however, we'll have an SDF to CapDL translator. So again, what the user sees is the ELF files, which they know how to build, and the SDF files, which he'll learn how to write. It takes about 15 minutes by reading the documentation online. And then, after the SDK is invoked, you'll be able to do several things. You'll be able to follow the old way, just get the init task as part of the core platform. Or you can go through the SDF to CapDL translator and get a generated CapDL, which is then checked against the semantics, the access policy corresponding to the SDF. More on that later. So this translation is not verified. The translated file is verified against the file you wrote. And the CapDL loader can then be used. Or, if you have more time, you can use the verified loader developed as part of the CASE project. And then you'll have to go through several steps of Isabelle and CamkES until this is built. But then you'll have verified system initialization. Now, this step is slow, very slow, like hours slow. So you wouldn't want to do this every time you build, because it will take ages. But the CapDL loader itself, the unverified version, is fast. So you'll be able to use both after the verification is done. The generated CapDL will be compatible with both. In fact, right now, it's only compatible with the unverified CapDL loader, and we'll see why in a second. Now, there's one thing missing from this picture. This guy acts as a monitor, right? It acts as a fault handler. These things do not do that. The CapDL loader loads the system and it becomes passive. It's not there anymore. Same for the case loader. So what will have to happen on the core platform side, we'll have to decouple this init task from the monitor. There will be an even simpler monitor implementation she'll be able to use that acts just as a monitor and not as an init task. And you'll be able to use the init task of your choice, one of which, again, will be verified. And this looks like a massive thing that would bring in the whole build system of seL4 But if we do our job right, you won't notice that it's there at all. It's not a promise. We're not there yet. You still have to know how this happens. But by the time we're done, we hope that you won't have to know about this part at all, and you'll still be able to use your own build system and just get the right system image out at the end and have the verified initializer inside it. Okay, so where are we with this? The NCSC-funded part of the project started in February. We have a working SDF to CapDL translator. It translates SDF to CapDL, but not yet fully featured. There's some missing features. And there's an SDF semantics, which is informally defined, not yet formalized. That's in progress. And there's a bit of an issue with the case loader as well. The case loader, which was developed as part of the DARPA case project, it exists, it works, but it wasn't done with MCS support. So, as you recall, seL4 CP is MCS only, whereas the case loader, as it currently stands, doesn't support any MCS features at all, which is a problem. So it might be that everything else comes first. We'll have our generated CapDL, we'll have our verified translation, and you'll still have to use the CapDL loader, which is unverified, until the case loader can be changed. That is probably not something that's coming in March. You'll have to wait a bit more for that. Okay, so just a few words on the verification for those who are interested in the formal matters. Our general idea behind everything we do is there are two things that need to match. The stuff that the users write, that's you, and the stuff that actually runs. What happens in between is not all that important, as long as we can prove that the meaning of the thing that actually runs and the meaning of the thing that the user wrote corresponds. And in the CAmkES-based CapDL loader, the case loader, we have that. The user writes CAmkES, it has an associated semantics access policy, and there's a proof that once you go down to CapDL and use the case loader, the running system will actually satisfy that. The difficulty is we can't just obtain this semantics by translating the SDF to CapDL. The SDF has no formal meaning as it currently stands, but it could easily be given a formal meaning. Just put it through the translator, and the CapDL has a formal meaning, and that's the meaning of the SDF. Unfortunately, as things currently stand, this semantics is obtained from CAmkES, not from CapDL. So we'll have to change that around a little bit before we have this correspondence. If everything goes as planned, March 2023. Except the case loader might not actually work at the time. But that means you'll be able to start developing. Use the old CapDL loader, and once it becomes available, your system will just work. You'll just be able to replace it with the verified case loader and have a verified initialization. That's the promise. That's the roadmap. The other thing that has to be verified is the library. Fortunately, the library is very, very small. It's got 8 functions in the API. That's the seL4 CP API, basically. It's got some handler loops, and it's mostly a thin wrapper over kernel calls. And for this, we plan to do something new. We plan to do SMT-based verification. This means no 170,000 lines of code, no 11 person years again. Again, it's not 170 now, it's more like 1 million. This part, fortunately, can leverage the kernel proofs, and hopefully we'll be able to do everything automatically so that if this library changes, we don't have to change the proof. And what sorts of things would we like to prove there? Well, We'd like to prove absence of undefined behavior, of course. That shouldn't be a problem. We can actually use the same C semantics that seL4 gets from the C parser for that. We've been experimenting with that. That seems to work. And we'll be able to reuse a whole lot of the SMT-based framework that we developed for binary verification for doing the actual SMT queries. We'd like to prove that the access policy is maintained. For that, we will need to have the initializer semantics first. We need to have the semantics for the system description to prove that whatever access policy that defines remains true no matter what library calls are made. And priority order processing and so on. The status of the verified library is not yet where I want it to be. There's two reasons for that. The first reason is human resources. It's currently just me. I'd need at least one student as well to make good progress on that. We have undergraduates coming in for the summer period to help with it, which should speed things up. So tentatively, we might be able to make March 2023 as well. We're on it, but it's not where I wanted to be in October 2022 for that. I think that's all I had to say about verification. And I think it's time for questions about either verification or the core platform. Thank you very much.
Hi, Zoltan. I have a questions about the verifications, the last slide of yours. Can you explain a bit? It's very high-level pictures about how to do the verifications. SMT, I know it. The C parsers, I know it. So proving the absence of undefined behavior, is that equals to proving the absence of runtime errors? Specifically, does that you mean you want to prove in a simple terms, you have a triple horse with a bang at the very end, and you want to prove true at the very end? So does that mean that the absence of undefined behavior?
Well, that's the bare minimum we'd like to have, right?
Okay.
Like that's one goal, obviously, which we'll need. But yeah, we plan to do a lot more than that.
Okay, but I'm interested with that part only because I'm interested with it. So does that mean that when you pass the code and then you have a bunch of guard provided by the C parser, you want to use the SMT solver to discharge all of these guards? Is that what you mean? If yes, can you share a bit about a little bit more technical how you want to achieve that?
So how this is going to work is that the C parser outputs. So we don't do things on the Isabelle side at that point. We're gonna export it into our graph language, which is similar to the one we used for binary verification, and then we're gonna generate the correctness conditions and the SMT queries from the graph lang itself. Now, I don't know if you've seen the graph language. It has an error node specifically in every function, and as a bare minimum, we'll see that node is never reached, no matter what happens. Okay.
Hi, Zoltan. Thank you very much for your talk.
Yeah, I found you.
So the future of building systems with seL4 is using the core platform. How will you allow users who've already built systems with, say, CAmkES to translate those CAmkES files into core platform files, or will you have to write them from scratch?
Well, I am hoping that it will not be my problem. So Kevin Elphinstone's been asking the exact same question for us. Will there be tools to do the conversion? I think there will be. I don't know if there will be verified tools in any sense. I'd wager not. But yeah, eventually we're going to have a good story on how you migrate your systems to the core platform. And again, it doesn't mean that you have to migrate all systems, right? You might want to use CAmkES for certain things, and you might want to use the core platform for certain things. Well, it's not up to me, Mr. Chairman, please.
Is there any support for cross-debugging, like as part of the monitor, for example? Or are there plans to implement something
Sorry,
like that?
which debugging?
Cross-debugging, so you have a remote debugger connected to your monitor. Would be good for application development, I think.
Yeah, that's.
But it's not on the plan yet.
I think it is. I think it is planned, right? And I think there's some features that enable it. Again, I'm not a core platform developer. I'm a core platform verifier, and I rarely, if ever, work with hardware. But I think part of the infrastructure is already there. Yeah. So you can see Ivan back there. He's wearing a white mask. He's your man, wave Ivan. On all sorts of questions like that, I think he'll know the answer. Okay.
All right, that's it for questions. Thank you very much again, Zoltan.
Well, thank you.